We have Bhavani and Zara, and they're setting up an experiment where they gently push trolley 1 down a slope and then it collides with trolley 2. They want to work out the momentum of the trolleys before and after the collision. Give a reasonable hypothesis for this experiment. They want to know what's happening before and after. So you have to say something about before and after. And a nice hypothesis would just be conservation of momentum. So the momentum before the collision is equal to momentum after collision. You need to write it out as a proper sentence because it is a hypothesis. To calculate the momentum, they need to find the velocity, but they only have a meter stick and a stopwatch. Explain briefly how they would find the velocities required. All that they're really doing is they're seeing, would you be able to conduct an experiment? So you should know that velocity is equal to distance over time. So they would measure the distance with a meter stick and the time with a stopwatch in order to determine the velocity. Aside from velocity, another measurement is required to calculate momentum. Momentum is equal to mass times velocity. So what would you need? You would need to measure mass. And what could you do that with? Either a scale or a triple beam balance or something along those lines. Bhavani and Zara use an inclined slope to compensate for one of the interfering variables. Now, one of the problems is something between the wheels and the trolley is friction. However, if I put a little slope there, I can counteract friction because friction is acting up the slope, and if I put a little component of weight down the slope, because remember there's weight acts straight down and it's got a horizontal and a vertical component, you will find that you would be able to somewhat counteract friction. So they're trying to get rid of friction. How does the use of an inclined slope compensate for this variable? So friction acts against motion. And with an incline, you will have a component of weight acting downslope. Bhavani and Zara find that they need to repeat the experiment several times in order to obtain reasonable results. How can they combine the results of the different runs to obtain a good result? Again, this isn't some epiphanal thing. They just need to average their results. And then, why is repeating the experiment a good technique to generally use? And they'd love some science in there. So, if many repeats are precise, remember precise is that they are close together, then probably the results are accurate. So it would have been lovely to see the words precise and accurate in your response. The diagram shows a car of mass 1,600 kilograms being used to test seatbelts and airbags when crashing into a solid concrete block at 20 meters per second. The manufacturers use crash test dummies for the crash test. For this car, the average stopping force is given. Convert kilonewtons into newtons, 640, 1, 2, 3. You must know your unit conversions. There are some videos if you need to revise them. And that's newtons. Calculate how long it will take for this car to come to rest in this crash. You have got all sorts of equations of motion information. And you could use that, or you can simply say that impulse, because you've been given force as well, is mv minus mu, and you substitute in this big fat force, and your mass is 1,600, and it's got to stop, and it started off at 20, and you find that the time turns out to be 0.05 seconds. Use the physics laws to explain how seatbelts and airbags work as safety features in cars. So seatbelts land up being the unbalanced force stopping inertia carrying a person forward in the case of a sudden stop. Airbags increase the time for the force, for the collision, or the change in, increase the time for the change in momentum, rather, from going fast to going slowly, or stopping. Therefore, they decrease the force. And of course, in that way, prevent injury. Cricket ball is thrown by Brenton from a boundary to the wicketkeeper. Brenton gives 50 joules of kinetic energy, and it reaches a maximum height of 12 meters above his arm. State the principle of conservation of mechanical energy. So that is a straight bookwork. So mechanical energy, which is potential energy plus kinetic energy, remains constant in a closed system. Calculate the speed at which the ball was thrown. EK is equal to a half mv squared. I need to convert that mass into kilograms, so I divide it by 1,000, and therefore, we've got the kinetic energy of 50, and therefore we can work out that V is equal to 25 meters per second. Then it says in speed, so it needs no direction. Determine the kinetic energy of the ball at the maximum height. So first let's look at the potential energy of this ball at the maximum height. EP is equal to mgh. And this is at the top. And that's equal to 0,16, 9,8, and they've told me a height of 12 meters. That turns out to be 18,82 joules. The total potential and kinetic at the beginning was 50, so therefore at the top the kinetic now is equal to the total mechanical energy minus what is potential, and I have still got kinetic energy going horizontally at 31,18 joules. Calculate the speed of the ball at the maximum height. I am now able to take that and say 31,18 is equal to a half mv squared, and that is going to be a half 0,16, and again I will be able to square root that v and get 19,74 meters per second. And obviously that's horizontally, because in the vertical direction it's stopped altogether. It's like projectile motion. Now we've got Sevesh. He's pulling a sled with parcels of mass 25 kilograms on them across the snow at uniform acceleration, and we get given the acceleration using a rope which makes an angle of 60 degrees with the horizontal. The tension in that rope is given, it's 100 newtons. Stating Newton's first law is again just bookwork. So, if a net force is applied to an object, the object will accelerate in the direction of motion. That acceleration will be directly proportional to the net force and inversely proportional to the mass of the object. Remember, you can use F equals ma, and watch me do it again. If a net force is applied to an object, that object will accelerate. That acceleration will be directly proportional to the net force and inversely proportional to the mass of the object. Calculate the horizontal and vertical components of the tension in the rope. And so we're going to sit there and we're going to say, well, we've got 60 over here, got a horizontal and a vertical, and we were told that this was 100. So that's my horizontal component, that's my vertical component, and vertical is opposite, so it's going to be sine. So that's 100 sine 60 degrees, and that's equal to 86,6 newtons, and the horizontal component is equal to, because it is adjacent to the 60 degrees, 100 cos 60 degrees, and that is equal to 50 newtons. Calculate the frictional force acting on the sled plus the parcels. So now this is where things get a little bit more interesting. I'll just move things up there. We now need to consider that only in the horizontal direction do I have a forward force as well as frictional force. So the forward force is only the 50 newtons. So force resultant is equal to the 50, which is big, minus the frictional force. And that is going to be 25 times, they've told me an acceleration, 1 equals 50 minus the frictional force, and therefore my frictional force is by coincidence also going to be 25 newtons against the motion. Calculate the magnitude of the normal force. Now we're interested in what's going on in the vertical plane, and so we need to say that the force resultant is 0 in that direction is equal to the weight which is acting downwards minus the normal minus, which acts against the surface, minus the fact that the sky is lifting it up in the sky, so minus 86,6. So 0 is equal to, my weight would have been 25 times by 9,8, minus my normal, minus this lifting force of Sylvestres, and I find that the normal force then turns out to be equal to 158,4 newtons. The next thing that we need to do is calculate the kinetic coefficient of friction between the sled and the snow. So we're going to say force friction is equal to mu force normal, 25, is equal to mu 158,4, and therefore mu turns out to be equal to 0,16, and it doesn't have a unit. We've got this train of mass 3 kilograms. It's connected by a string to a wagon of mass 2 kilograms. Tanzania fastens a cable to P and pulls it with a force of 12 newtons at an angle of 50 degrees with the horizontal as shown. The train moves over a wooden floor from the rest position. A frictional force of 2 newtons acts between the engine and P and the floor, whilst the wagon experiences a frictional force of 1. So we've got 1 there and we've got 2 over there. Draw 2 separate fully labeled free body diagrams. Now remember, our free body diagrams are going to be a dot and then everything coming off that dot. So first let's do the 2 kilogram. There's tension in the string going forwards, and there is friction acting backwards. They only want the horizontal forces, so only put the horizontal forces. The next one, there's going to be the component of 12 newtons applied force. There will be tension acting backwards, and there will be friction acting backwards. Or frictional force is better, I suppose. Tension force would be better, but okay. Then you're going to calculate the magnitude of the acceleration of the train, and this is where you put everything together. So force resultant for the 2 is going to be tension minus the frictional force. Force resultant is 2 times the acceleration of the system. I don't know the tension. I do know the frictional force is 1. Simultaneously, the force resultant of this 3 kilogram is going to be equal to the component of 12 minus the tension and minus the frictional force, which I happen to know over here is 2. And if I want to get this component of 12, I can work it out. Force horizontal, there's 12, there's 50. So I'm going to look at the adjacent side over here, and that means it's cos, so I'm going to say 12 cos of 50 degrees, and that turns out to be 7,71 newtons. So I have got 3 times an acceleration I don't know, 7,71, minus a tension I don't know, minus 2. I can then put both of these in terms of t. T is equal to 2a plus 1. Here, t is equal to 7, well, it's 5,51, at least 5,71, isn't it? 5,71 minus 3a. Now, if we're going to solve for those, they become 2 simultaneous equations, and we can solve for them, and we can find that 2a plus 1 is equal to 5,71 minus 3a, and a turns out to be 0,94 meters per second squared, whilst t, when I substitute back in, is going to be equal to 2 times 0,94 plus 1, and that is equal to 2,88 newtons.